All right, welcome. Let's jump right into a deep dive masterclass on a topic that is absolutely crucial for your competitive exams. Whether you're aiming for TNPSCAE, SSCJE, RRBJE, GATE, or the ESC, we are going to completely master Moment of Inertia today. We're going to start from the very beginning and build all the way up to the applications you will see on your papers, so you can lock in those essential marks. So, what's our game plan? Here's the roadmap. We'll kick things off with the most important rule of them all, the Parallel Axis Theorem. Then we'll use it to master shapes like triangles, circles, and semicircles. After that, we'll dive into a numerical challenge, see why all this math actually matters in the real world, and then we'll finish up with an exam victory lap to make sure you remember the key takeaways. Okay, first things first, we are starting with the single most powerful tool in your entire toolkit for solving moment of inertia problems. It's called the Parallel Axis Theorem, or PAT for short. Seriously, if you can master the logic we're about to go through, you'll be able to solve almost any question they throw at you. Now, this is the standard formula you see in every single textbook. It's amazing because it lets us find the moment of inertia, which we're calling I, about pretty much any axis we want, as long as we know our starting point. And that starting point is IG, the moment of inertia about the shape's own center of gravity. It's centroid. But, and this is a huge but, this is where so many people make a critical mistake during the exam. So this leads to a really interesting question and a common trap. Let's say you've memorized the formula for the moment of inertia about the base of a shape. It kind of feels like you should be able to use that as your reference, right? Can you just plug that into the theorem and find the MOI about some other axis? Well, let's put it to the test, because this is a classic trick you'll see in exams. And the answer is a big fat no. Here it is. The single most important thing to remember, the golden rule. The reference axis in the parallel axis theorem, that IG, must always, without exception, be the axis that passes through the centroid. You can only use this theorem to move away from the centroid. You can't use it to move from some other random axis. This is non-negotiable. Okay, now that we have the golden rule down, let's put it into practice with our first shape, the triangle. I can almost guarantee you're going to see questions about this, so let's break down exactly how to derive the formulas you absolutely have to know. This process is just beautiful. We start with the one formula you absolutely must memorize, the moment of inertia about a triangle centroid. This is a standard formula value. It's always BH cubed divided by 36. Now we use our golden rule, the parallel axis theorem, to find the MOI about the base. The distance, d, from the centroid to the base of a triangle is another standard dimension you should know. It's h divided by 3. We substitute everything into the PAT formula, do the math, and we arrive at our final calculated result for the base, bh cubed divided by 12. And hey, don't think this is just some abstract theory. This exact formula, this exact question, was pulled directly from the TNPSCAE 2015 exam paper. Knowing how to do these derivations isn't just for practice, it translates directly into getting you guaranteed marks. So let's wrap up the triangle. You need to have these three formulas locked in. About the centroid, it's BH cubed over 36. About the base, it's BH cubed over 12. And about the apex, it's BH cubed over 4. But notice the pattern here. The moment of inertia is always at its absolute minimum value when it's about the centroidal axis. The farther away you move the axis from the centroid, the bigger that MOI value gets. All right, let's move on to curved shapes. Now, I know the formulas can look a little more intimidating with the pi symbol showing up, but don't worry, the logic, the process we just used with the parallel axis theorem, it's exactly the same. For a semicircle, here are the key values to remember. First, the centroid location from the flat base is a standard formula value. It's 4r divided by 3 pi. Now, a common value to memorize is the MOI about the base, which is another standard formula, pi d to the 4th divided by 128. We can then use PAT to work backward and find the MOI about the centroid, which gives us a calculated result of about 5 pi d 4th divided by 128. Oh, and you should also just memorize the MOI about the vertical axis, which is a standard formula of pi d to the 4th over 120. Knowing these can get you 2 to 3 easy marks. A full circle is actually way simpler, all thanks to its perfect symmetry. The moment of inertia about any axis that passes through its center is exactly the same. This is a huge standard formula value to memorize, pi d to the 4th divided by 64. Now, if we want to find the MOI about its base, which is just a line tangent to the circle, we just apply our trusty parallel axis theorem. That calculation gives us a final calculated result of 5 pi d to the fourth divided by 64. Okay, what if you have a hollow shape, like a pipe or a hollow rectangular tube? The logic here is actually really straightforward and kind of cool. It's just subtraction. You pretend the shape is solid, calculate the MOI for that big outer section, and then you just subtract the MOI of the inner missing part. The only rule is that this trick only works if the shapes are concentric, meaning the centroid of the big shape and the centroid of the whole are in the exact same spot. So, theory is great, but you don't get marks for theory alone. You get marks for solving problems. So let's take everything we've learned and apply it to a typical exam-style numerical problem. We'll walk through it together step by step. Okay, let's get into the numbers. We'll use some assumed values for this example only. Let's say the width is 120 millimeters and the depth is 200 millimeters. Step 1, we find the centroidal MOI about the x-axis using the standard formula for a rectangle, b d cubed divided by 12. Step 2, we plug in our assumed numbers and we get a calculated result of 80 million millimeters to the power of 4. Step 3, now we use the parallel axis theorem to find the MOI about the base. We take our IX and add the area times the distance squared. The distance is just half the depth, or 100 millimeters. Step 4, this gives us our final calculated result for the base, 320 million millimeters to the power of 4. So, after all of that grinding through calculations, you're probably asking, so what? Why do we care so much about this number I? And the answer is, I is everything. It is the absolute backbone of structural engineering. Let's take a look at where this value I shows up in some of the most important formulas you'll ever use. Check this out. In the formulas for bending stress and for beam deflection, where is the I? It's in the denominator. It's an abasement. This is so important. It means that the bigger your I value, the lower the stress will be and the less the beam will bend or sag. That's why we use I-beams. Their shape is genius because it pushes the material far away from the center, which maximizes the I value and makes it incredibly stiff and strong. Now let's flip it and look at columns, which are under compression. In Euler's buckling formula, look where I is now. It's in the numerator. This means a higher moment of inertia directly increases the amount of load a column can take before it just gives up and buckles. So whether you're trying to resist bending or resist buckling, I is the number that tells you how well a shape is going to perform. Look, if you forget every single formula we talked about today, please just remember this one thing. Moment of inertia is just a fancy engineering term for a shape's resistance to bending. That's it. Think of I as a bending resistance score. A high I means the shape is really stubborn and hard to bend. A low I means it's flimsy. Simple as that. All right, it's time to bring it all home. Let's do a quick victory lap. These are the final must-know points that you need to have locked and loaded in your brain before you step into that exam hall. This is how you secure the marks. Listen up because these are the top 3 mistakes people make. Number 1, trying to use the parallel axis theorem from any axis that is not the centroid. It's a fatal flaw. Don't do it. Number 2, mixing up your triangle formulas, like bh cubed over 12 and bh cubed over 36. Write them down and memorize them correctly. And number 3, getting the units wrong. Moment of inertia is always length to the power of 4. I want to be crystal clear about this. Just by memorizing the standard MOI formulas for a rectangle, a triangle, and a circle, you are basically guaranteeing yourself an easy 2 to 3 marks on your exam. This is the lowest hanging fruit you can possibly pick. It's free marks. Don't leave them behind. Okay, here's your final checklist. Let's run through it. 1. The parallel axis theorem only works from the centroid. 2. Moment of inertia is always at its minimum value about that centroidal axis. 3. MOI is just a score for how well a shape resists bending. 4. The unit is always length to the power of 4. And 5. In beams, a bigger I is always better. It means less stress and less sagging. Got it? Good. And so I'll leave you with this final thought to chew on, something that gets to the very heart of what engineering is all about. Now that you know how to calculate a shape's resistance to bending, how would you go about designing the most efficient beam you possibly could, one that gives you the most strength for the least amount of material? Think about that. Thank you for joining me on this deep dive. Study well, stay motivated, and go conquer that exam. And hey, don't forget to subscribe for more explainers just like this one.